Okay, hello everybody. So I'm going to introduce myself more in a moment, but first I want to show you what we're going to talk about in this talk so that you can manage your expectations. So first of all, sorry, my preview is a little bit small. So we're going to look at why and how Python uses low-level programming languages, which I think is going to be more interesting for novice Python users. Considering the amount of hands that were raised when I asked how many people have written C++ code, I'm going to go fast on this part because I think most people are already up to speed with that. Then we're going to talk about how that interoperability with lower level programming languages impacts the creation and usage of Python packages. And then which is going to be more interesting for more experienced Python users. And then I'm going to look at some Python package index stats, just a couple, and discuss some potential future ideas for Python packages. And I think this last point is going to be especially interesting if you see yourself as a Python community member. So not just a voiceless, anonymous user of the Python language, but also somebody who is part of the community discourse and maybe who can, I don't know, even influence it a little bit. So yeah, my name is Loris Crow. I'm VP of Community at the Zig Software Foundation. And I have a small YouTube channel. I also live code on Twitch. So if you're interested in seeing somebody write some Zig code, check me out on Twitch. I will probably, once I come back from PyCon, I will probably go back to writing my own static site generator. I have opinions, especially about templating languages. So I'll go do that. And lastly, I also organize a conference in Milan called Software You Can Love. We had one a few weeks ago, and hopefully we're going to have another one next year. So,
just last week,
oh, last week. Oh, yeah. Anyway. Anyway, some disclaimers. So I have written a bunch of Python. I've started using Python in university. My coursework was in Java. I didn't care. I did mine in Python anyway, and it was a huge productivity hack. My first paid job was in Python. It was like a Django application. So I've done a bunch of Python. Also, I did bioinformatics afterwards, some more Python. But then life happened, and I parted ways with Python. So I have some experience with Python. Also, this awesome T-shirt that I have, duck typing. As you can see, there's also a banana peel. This one comes from a PyCon in South Africa. But I am bringing to you like a bit of an outside perspective. I am part of the Z community. I know of some things that we've done, and I'm kind of like bringing you gifts in a sense. And that means also that it's up to you to decide if you like these gifts or not. So like I will make some statements, some claims, and ultimately, though, it is up to you to decide exactly how well they suit your use case or not. Lastly, despite the title, this is not a critique of the wheel package format. I know that it's like Python wheels are like zip files, they have an internal structure, etc., but I'm not going to critique that. This is more high level. So why does Python rely on low-level programming languages? Usually people say, well, because Python is slow. There has been a keynote also explaining about exactly how, to what degree that is true or not, etc. But I don't like it as an answer because I feel like it's imprecise and also like feels like a criticism. Like you say, oh, well, because it's slow. And I feel like we can do better. And I'll try to provide you with two reasons, in my opinion, why Python relies on lower level code and on lower level programming languages. And the first one is because Python targets a virtual machine, not the hardware. So when you write Python code, you're pulling levers inside of a virtual machine, and the language syntax makes it easy to do that. And it doesn't make it as easy to instead have precise control over the hardware because of the way Python is designed. You pull levers in the virtual machine, and then the virtual machine worries about making that happen on any specific piece of hardware. So that's nice because that also means that in Python you can easily do things that otherwise would be hard to do if you only had like C. If you were writing C, some of which can be problematic, as the keynote showed. But yeah, the flip side is that whenever you need instead precise control over the hardware, then Python is not going to be particularly good at giving you that level of access. And that tends to be the case, especially when you care about performance, because performance means making sure that the machine does exactly what it has to do to perform the operation. And like, it's not just a matter of obtaining the right result. It's also how you do it also matters. The second reason it's connected to this one, like the second reason why Python relies on lower level programming languages But in my opinion, it's distinct enough to deserve a separate bullet point. And that is that very sophisticated implementations of algorithms are written in low-level programming languages. Like there's a bunch of complicated, sophisticated libraries that have been implemented in C, and you want to reuse that. And so you have to be able to access that implementation. In theory, you could spend a bunch of effort and write this stuff in Python, but the reason why people use C and C++ and lower-level programming languages is because these languages act as a form of like lingua franca among other high-level programming languages. Like if you were to write this stuff in Python, like if you were to write like a super complicated matrix multiplication, image processing, whatever algorithm, you write it in Python, then only Python can use it. Well, in theory, other languages could spin up a Python VM, but like the whole point was performance, and now you're doing weird stuff to make it work. So it obviously makes more sense to write this stuff in C. So in a sense, it's a way of getting more mileage out of effort that other people have spent. And this is kind of like the same boat in which all high-level programming languages are. All high-level programming languages make it easy to do high-level stuff, not as easy to do lower-level stuff, and they all then tend to rely on C and C++ mainly. But not only, there's also Rust, like in the previous talk, there's also NIM, and some others. Fortran, of course, also. In any case, so how does Python rely on low-level programming languages? The talk before also got into more details here. I'm just going to give you like a super high-level overview, but the idea is like if you're a package author, you use C types, CFFI, which is both the name of the concept of having a C foreign function interface system, and also the name of a package that actually offers that functionality in Python. And so that way your C, C++ code can interoperate with Python. The C, C++ code that you wrote has to be compiled to a dynamic library, and those dynamic libraries are machine code, so they're specific for the combination of OS and architecture that you have, and some more. We'll get into that in a moment. And then CPython, the interpreter, or actually whatever interpreter you have, loads that stuff at runtime. Different interpreters might have different rules, so not all interpreters can load dynamic libraries, or if they do, not necessarily the same way, but roughly speaking, that's how it works. And lastly, obviously, package authors also write Pythonic bindings so that their users don't have to deal with all the annoying lower-level C interoperability stuff. Great, this works. It's beautiful, it's perfect. End of my talk. No. No, it would be nice. Instead, welcome to C toolchain hell. Because if you were to make a package like this and you wanted your users to install it, well, now there's a few problems because they need a C, C++ compiler instead. If they don't have it, installation fails. Different platforms have wildly different setups, both in terms of the compiler itself, like all the major compilers, they all have quirks, but also their setups are very different. And that also adds complexity and jankiness to this process. Also, your users need build dependencies, and that is usually something that requires, basically makes your package depend also on other package managers. This is what happens whenever you have to install, like you do apt install lib this, lib that, or foo-dev, all these packages, these are all other dependencies. And so this thing is a mess. Also, these dependencies have dependencies of their own. Normally, the package manager deals with that, except when it doesn't. Then things get really funny for everybody except the user. So this is a problem. And so Python solved it using wheels. Python wheels to the rescue. So Python wheels can contain pre-built dynamic libraries. And this solves all the previous problems because users now get a pre-built binary. They don't have to build it themselves. They don't need build dependencies. They don't need C++ compiler. They don't have weird systems where things don't work for whatever reason. But wheels don't solve all problems because now you're distributing binaries, which thankfully is totally unexploitable. Can you imagine somebody exploiting a binary committed to a repo or something, like to add a backdoor to all SSH servers? Oh my God, that would be hilarious. Thankfully, it has never happened. But one day, who knows, it might happen. Then there's also other runtime dependencies. So the problem is, like, you're trying to avoid the complexity of C and C++, and as you try to escape, some of it still reaches and grabs you by the leg, because your DLF, like your dynamic libraries, might depend on other dynamic libraries. And this is where tools like audit will come in, where basically they look at your dynamic library, look at other dynamic libraries that it references, and copies also those into your wheel. Has anybody here ever used audit wheel or similar tools? I see a couple of hands. Thank you. You're doing a lot of work for everybody else, and they don't even know about it. But the thing is, like, the process is still complicated, and like there's some complexity that it's still bleeding through this system. You're trying to simplify the process, but some complexity bites back. And then there's another problem. For the people who were at the philosophy and software talk, Cartes? I don't remember. The cart was mentioned. Well, guess what? This is the Cartesian product of a bunch of sets. So to make pre-built binaries that work for everybody, you need to pre-build it for every CPU, every OS, every ABI. I'm not going to get into what ABIs are. Actually, people here already probably know. And there's also different Pythons. And these are like all the tag systems that the Python package manager uses to determine which is the correct wheel for each user. And so now you have to do ARM, Windows, ARM, Linux, ARM, Mac, Intel, Linux, Intel, Windows, Intel, Mac, et cetera, et cetera. And it's a lot. And then you have different versions of the OSs. Maybe Windows 10, Windows 11, not much of a difference. But man, whenever Mac updates, things break uncontrollably. And so you need to build a new set of wheels for a new version of macOS. And then there's Linux. So Linux has versions. But it doesn't just have versions, it has distributions. And every distribution is a beautiful snowflake, unique in its own way. And that means that your stuff compiled for Ubuntu Linux, it is not gonna work on every other distro. It will work on some, but it will not work on others. NixOS, for example, is particularly funky from that aspect. So, and so this is when the many Linux tag was added. There's a PEP that adds it. Basically, many Linux, like you can use the many Linux tag to create a wheel that targets a subset of kernel, syscalls, and like other things that tries to be as compatible as possible with as many Linuxes as possible. Doesn't cover all of them, but it does cover some. And to build for many links, there's like VMs involved. So there's a bunch of complexity over there. But this is where I'm starting to kind of, I don't know, starting to be disappointed by this way of doing things, because we set out to do two things, right? Use other people's work, we are still succeeding, but also get performance out of it. And here we are starting to make some compromises, right? Because if you lose many Linux, you're like purposely cutting yourself off of improvements in the kernel. There are different versions of many Linux. Like I believe the one that is still mainly used today, I believe, I might be wrong, but I believe it cuts you off of IO ORing, which is like a set of syscalls that have been added to Linux that are actually improved performance of networking, file access, everything async related dramatically. And so for compatibility, you're cutting yourself off of all these improvements. CPUs, I mentioned Intel and ARM, 32-bit, 64-bit, but it doesn't end here, right? Because you also have CPU extensions. So for performance-sensitive code, having AVX, SSE, and all these other extensions for vectorized operations enabled does make a huge difference. And now you're also leaving that on the table. Or if you don't, now you have, I don't think that will actually support that, like the ability to select which flags your CPU has. So I don't think it works. But even if it did, now you have an even bigger combinatorial explosion of wheels that you have to create. So, and all of this is because the freaking C compilation toolchain sucks. And like, you're trying to solve it, but the problem is, if you could get reliable builds, then you wouldn't have to do all of this stuff in the first place, or at least it would be like a different picture. And this is where Zig comes in. So Zig is a compiler toolchain that not only can compile Zig, but it can also compile and cross-compile C and C++ code. I'll get to that in a bit. I just want to mention one thing first. I work at the Zig Software Foundation, so it's a 501c3 non-profit corporation, just like the Python Software Foundation. We don't have any big tech board member. We don't have any venture capital investment. I paid out of my own pocket to be here today. And my point is that for once, you're not looking at a startup product that is trying to get a quick exit, but we're actually here to try and improve the state of computing for real. So let's get back to the technology. So Zig, this is what we put on the website. Zig is a general purpose programming language and toolchain for maintaining robust, optimal, and reusable software. We do mean every single word in this sentence, but the one that is most interesting in this context is the one that says toolchain. So let me tell you about the toolchain. So first of all, the Zig compiler can also cross-compile C and C++ code. And that is huge, especially cross-compilation. So if you take a C compiler or a C++ compiler and you try to compile from Linux to Windows, out of the box, it's not going to work. If you try to compile from ARM to Intel or vice versa, it's not going to work out of the box. With Zig, you can. Not only with Zig code, but also with C and C++ code. You can target any platform from any platform, with some caveats, but it really works. And the reason why this works is that, for example, one thing that Zig does is that it bundles all the libcs, all the glibs. It also so glibc, muscle, wasylibc, also Windows, etc. And for glibc, it also bundles every single version of glibc. Maybe not the super old ones, but like the reasonably recent ones. They're all bundled, and so you can target a specific version of glibc, which maybe some people here understand when this is important, or rather have been bitten by what happens when you don't. And there's also a bunch of other tools that come with the Zig toolchain that help you with cross-compilation. And Zig is an in-place replacement for Clang. Like it's command line, it's flag compatible basically. So every time you invoke Clang, you can replace Clang with Zig CC, the CC subcommand, and it should work. And it's also not a separate compiler, just so we're clear. Zig bundles Clang, so you get the same compilation characteristics that you get from Clang, but there's also a lot of stuff built on top that does things that Clang cannot do out of the box. And I actually only mentioned some. There's a lot more. Another kind of important thing is that Zig doesn't rely on system-wide settings unless you want it to. So you can create, builds that are like consistent and reproducible, and not, oh, it only builds on my machine anymore. Also, Zig has a build subcommand, Zig build, which is a build system that can replace make, cmake, so you can also get rid of those dependencies. And it can also download dependencies. So the package manager can fetch and build dependencies for you. And this is all in a 40 megabyte dependency-free tarball. And it actually works. It's still work in progress. We are not v1.0. The language is still very in flux, but the toolchain is very solid. And for example, Uber is using it to compile their entire code base. Uber has a big Go monorepo, but they also have a ton of C dependencies. Some they wrote themselves, some are like usual open source stuff that they depend on. And C-Go can interface with C, but Go doesn't compile C code. It certainly doesn't cross-compile it either. So they basically were able to port their entire infrastructure to ARM by using Zig, and they still do today. There's like a Bazel packet, like a Bazel package that does this, that they developed. And yeah, this is awesome. And actually, you can get the same power in Python. Pip install Ziglang, and it works. You get Zig. Let me read you the rationale for this. So, although Zig is useful in itself, the Zig toolchain includes a drop-in C and C++ compiler, ZigCC, based on Clang. Unlike Clang itself, ZigCC is standalone. It does not require additional development files to be installed to target any of the platforms it supports. Through ZigCC, Python code that generates C or C++ code can build it without any external dependencies. And this is how you make your build actually, portable in a sense. Then I said I wasn't going to trick you into writing Zig. I lied. If for any reason you also do some development, there is packages like ZigPy does, or more in general, we like to say in Zig that it's easier to use C libraries from Zig than it is from C. It's a bit of a strong claim, but if you catch me after the talk, I'll be happy to show you some evidence of that. So, in light of what you can do with Zig, here's the updated workflow. Use Zig in your setup.py to build your C, C++ Zig code. Zig can do also the fetching and the building of other build dependencies without relying on any system-wide setting. And so it's just Zig build. And actually, that's what I do. Like my static site generator, it's mostly Zig code. Well, actually, I'm not sure. It's certainly partly Zig code, but I also depend on tree-sitter for syntax highlighting. I depend on the CMark, Markdown parser. These are C libraries. I don't care. I have the build script set up. I just do Zig build, and it works on any machine. And yeah, so one caveat of using Zig to manage your dependencies is that, well, those dependencies need to have been packaged for Zig. Not every single C package out there has been bundled for Zig, or C++ have been packaged for Zig. So although there's a surprising amount of repositories that have like a build.zig file in them, but not all of them have them. But at the same time, in the Zig community, we have like an organization that we created called All Your Code Base, for those who know the meme, where we maintain our own build scripts so that people don't go annoy and harass the package maintainers to have them add a build script. So we do it ourselves. And yeah, lastly, those dependencies need to be distributable. If you don't, like, if the license says that you cannot redistribute them, then I mean, sucks to be you. Don't use proprietary software if you can. Well, congratulations, you do this, and your build is now consistent and optimized, because if your users download this and build it on their machine, if they have AVX or whatever instruction, then it's going to work on their machine. The executable will be able to leverage those instructions for better performance. And at that point, you can choose whether you want to offer pre-built wheels or not, because my point is not that wheels should like go away and you should never pre-build binaries. Absolutely not. But there is a mentality shift from, oh, I have native dependencies, I must produce all the wheels, to now I can choose based on my specific situation. For example, the Ziglang package itself, spoilers, it's a wheel with a bunch of pre-built versions of Zig in it. Why? Because Zig depends on LLVM, so to compile Zig, you need to compile LLVM. That takes a bunch of gigs of RAM and like half an hour even on a decent computer. So yeah, no point in doing that. Let's distribute wheels. But not every single project that has native dependencies has the same situation. And actually, maybe so if you're thinking about big things like TensorFlow, you probably don't want to build TensorFlow on your machine when you install a package either. Fair. But you could have stuff like parsers that have like a native implementation of the parser logic, which can benefit greatly from vectorized operations. And that takes like a blink of an eye to build normally. So I'm suggesting you to add stuff to your setup.py script. And there's a real Python article about Python wheels, which I read, and I think it's fairly informative. I liked it. But there are a couple of claims in it. There's a bunch of claims in it about advantages that Python wheels have. I don't have an issue with most of them, but with a couple I do. So I would like to debunk them, because also I've seen them written elsewhere. So one says, wheels cut setup.py execution out of the equation. Installing from a source distribution runs whatever is contained in that project setup.py. As pointed out by PEP 427, this amounts to arbitrary code execution. Wheels avoid this altogether. Now, I'm not sure I understand the point here, because, like, sure, you don't run this out of the py, you're just running my binary blob that you have no idea what's inside. So I don't understand exactly the nature of this claim. Anyway, the second one is wheels are smaller than source distributions. For example, the 6th wheel is about 1/3 the size of the corresponding source distribution. The rest of the point is not super interesting. Now, this is another claim that I take issue with. So first of all, the example brought forward, the 6th wheel, if you click that link and you actually go take a look, the source distribution is bigger, sure, than the wheel, but it has documentation in it. So there's the source code and a bunch of docs, like 30 kilobytes unextracted worth of like RST files. And the wheel doesn't have it. And the difference in any case is like 30 kilobytes for the source distribution and 10 kilobytes for the binary wheel. So it's like a 20 kilobytes difference. And so the example, in my opinion, is comparing apples to oranges, so it's not relevant. But also the bigger claim that like a binary distribution is bigger than the source distribution, that is, I would say, that based on my experience, you cannot say this with in an absolute sense. Sometimes binaries are bigger than the source, sometimes they're not. It goes both ways. It's not as clear cut. But most importantly, I feel like this bullet point is absolutely misleading, because this is not a one-to-one situation. You don't have the source distribution and the wheel. You have the source distribution and a fan of wheels for all the platforms that you need to support. And that is actually shown really well if we look at a couple of stats from the Python package index. And the background could hint at what's going on there right now. So the Python package index is right now 85 terabytes big. and it's growing fast. So you can take a look. That is awesome. So congratulations. The Python community is clearly very active and producing a lot of work. And actually, it's not going to, like, if you look at the growth, it's not going to take long to reach and surpass 100 terabytes. Great. But then if you look at the split, 3/4 of all that data is binary data. It's wheels. And it makes sense, right? I mean, you have to build all the freaking combinations of targets, platforms, etc. So it's what you would expect. So this should, in my opinion, finally debunk the real Python claim. But I also would like to add another couple considerations about this. So first of all, disclaimer, I am not affiliated with the Python package index. I don't know anybody that works at the Python package index, or if I know them, I don't know that they do contribute to that. And I don't know their financials. But Python is a big community, it's one of the leading languages, so surely they're going to be fine financially. That said, those costs still exist. Like if you do some math and you look how much it's going to cost you to put 85 terabytes of data on S3, that is big numbers, right? We were trying to ballpark it. It's like 6 zeros, right? So big numbers. And the idea is, of course, there's going to be a bunch of big tech companies that are going to chip in. They're all going to be sponsors, participate. Assuming these things are actually on S3, AWS is most definitely going to give out a bunch of free credits to people. The problem is the costs. So for once, on one hand, the costs still exist. So if they didn't exist, all the same exact money could be moved somewhere else to solve some other problem that, or the thing that you would like to have improved. And the second point is that even if you're getting free money for this, man, it is very nice to be independent as an open source community. Every time a big tech does something that you don't like, if you're not financially dependent on them, you can speak up. You can say that they suck. You can speak your voice. If instead a big tech company does something that you don't like and you depend on them financially, then yeah, all you can do is stay silent and smile, because otherwise you're gonna get hit by the 6-0 AWS bill or whatever next month. So this is something that maybe it's not a pressing need, but it's not something that should be taken for granted, in my opinion, if you want to build a healthy community. And in the Zig community, for example, well, in the Zig project, we have the standard Zig Software Foundation offer for big techs and venture capital, where we say, sure, you can offer us how much money you want. What we're going to give you in exchange is 0% ownership of the organization and 0 board seats. Thank you very much. So when I say reinvent the wheel, here's what I'm trying to suggest you try out. First of all, try to perfect your source distributions using Zig. This is something you can do independently on your own today already. See how it works for you. Maybe it works, maybe it doesn't. Maybe you're going to hit like a bug, an issue, something that we haven't solved on our end. If so, maybe reach out, open an issue on our repository, talk with us. We're definitely interested in helping other languages solve their toolchain problems. Another thing as a user is maybe consider preferring a source distribution over a wheel if the build times are worth it. So if it's not TensorFlow, if it's not something that takes forever to build, and you suspect you will get some mileage, out of having extensions enabled or some other thing specific to your specific machine, do it. Beware though that there's like all these CIs that run on containers. You start with a base image. First thing you do is pip install a bunch of packages. Beware that if you do this and you put all the extra flags to prefer the source distribution, so to compile stuff over installing the binary, that is going to slow down your CI, so you should cache that layer of your CI. Be smart. I would micro rent. That is also consider doing that anyway, because it can be annoying for projects having CIs keep downloading stuff forever. We, as the Zig project, we have people that start downloading Zig a lot, and we're starting to have like a bill that we went past our free tier of S3 a while ago, and we also got tired of kissing ass to AWS people to get free credits from them a while ago, so it's a bill that we have to pay. And we know that a bunch of those downloads do come from just CI downloading Zig over and over and over and over, so be mindful of that. For people who are involved with the Python package index, here's an idea. Do evaluate if and when to add a cache package model. The idea is this. Today, if you delete wheels, it's a problem because you're not gonna, even though you might have the source distribution, it's not trivial to get from the source distribution to the built wheel. But if you make it trivial, like if you can make it consistent, like one command and it always succeeds at building for whatever target, then your wheels stop being data that you lose, well, that if you delete, you lose data, and instead become like a cached artifact that you can delete at will, and you could even decide that you're gonna allocate, I don't know, 50 terabytes or whatever memory to cache the most commonly used wheels, well, source distributions that have like a build step, like a C compilation step, and not the rest. And like you get a lot more flexibility. And this is how other package systems work. For example, Nix. The Nix package manager, you tend to build things from source, but there's a Nix cache system that basically allows you to speed up if you're building something that has already been built by a bunch of other people. And that's good. And more generally, so I used to have in the original draft of this talk, I had like a pretty lengthy rant about containers. I cut it, but I have some remnants. So my point when I say they invent the wheel is try to improve the state of Python packaging by embracing advances in systems programming and not by just saying, oh, there's this problem, I'm just going to slap a container on it. Because I feel like that solves the problem somewhat short term, but it's not a real solution. I even have a video for this. Let's see if it loads. It does. Right. Oh, no. My C toolchain is crap. Let's put Docker on it. Problem solved. Thank you very much.
Thank you very much. This was amazing. So, distributing the Zig compiler as a wheel is nice, but it is still disturbing a binary blob. Distributing a binary blob. If Zig gets compromised, a lot of packages would be infected.
Yeah, absolutely. 100% you're going to get pwned. Sure. Still, it's better to have one. It's still better to have one point of failure than have every single package you install be affected by the same issue. That said, it's a minor bullet point. Like if it was only a security problem, I don't know, I wouldn't have bothered with this talk, to be honest. I feel like the actual problems of having the communities shoulder costs that maybe they could avoid and getting actually the performance that you should get out of all the effort that you have to go through to get to be able to depend on lower level programming languages, I think that is more important and the main reason why I'm here today.
Thank you. And another question, what about Cosmopolitan?
I don't know, can you actually build, has anybody ever built a wheel that uses Cosmopolitan libc and can actually do fancy stuff with it? I don't see any hands. So Cosmopolitan libc is an interesting libc that does some clever tricks to basically create one executable, and that same executable can be run on different systems, even different CPUs. It's mind-blowing. But I would say it's a very clever trick, but I think it has some, it offers some things that are still a little bit brittle and problematic once you're just trying to get stuff to work. But it is cool, but we don't bundle it today, maybe in the future.
Would the thesis of this talk, switching to portable build systems to avoid shipping binaries, have been possible without Zig leaving the LLVM ecosystem?
So this is a reference to the fact that we today are depending on LLVM. So if you want to compile Zig, you have to compile LLVM first, and we want to stop doing that. The way this is going to work is that we're not ejecting ourselves forever from the LLVM ecosystem, goodbye, and make our own compiler from scratch, and that's it. But what we're going to do instead is work on our alternative, but still be able to use LLVM through the Zig package manager. So instead of having LLVM bundled inside of the Zig executable, what you're going to do is have Zig produce LLVM bytecode, and then invoke LLVM, like get LLVM as a package, and feed the LLVM bytecode to LLVM to obtain an optimized executable. So long story short, nothing is going to change for the end user. It's just going to be, it's just going to work in a slightly different way in the internals.
So there's this question: how far is Zig from getting rid of LLVM, and more importantly, where I can buy the tool at the end to avoid cleaning the dishes?
So the tool at the end, I think you can go to, I don't know, docker.com. As for Zig getting rid of LLVM, as I explained, we have a transition plan. We're not trying to just nuke LLVM and get renounce or like say no to all the benefits that we get from LLVM. We are working on it. We are right now very close to the point where we're going to be able to do debug builds of Zig programs without invoking LLVM. Very, very close. Not for every platform yet. For, I believe it's going to be, the first platform is going to be like x86-64 Linux. That's going to be the first one. The next ones, the other ones are going to come next. But that is the closest milestone right now. So we're going to do it first for debug builds so that you can have instant debug builds, because right now, rebuilding Zig programs takes a while, and most of the time is spent in LLVM, which is fine if you're optimizing, but it's not fine if you're making a debug build. And so we're aiming for like very fast debug builds right now, and then we're going to do incremental compilation. Right now, Zig builds everything. Zig, not C. C has different compilation units, but the Zig code has one compilation unit that and everything gets rebuilt every single time. There's no extra granularity. We're going to do full incremental at the single top-level declaration level, and that's going to ideally net us pretty much instant rebuilds for arbitrarily large projects. It's pretty cool.
Is there a way to know in probably in advance, how big is the gain in terms of switch to Zig build toolchain?
In terms of like jankiness, humongous. Like the amount of jankiness that you get rid of. In terms of like performance, as in like how much performance gain you're getting from like building on the user machine versus downloading a pre-built wheel, it wildly depends on the application. And I would actually say probably for most people, it is not going to be that interesting. But for some people, it will be dramatically so. It really depends on the use case.
How far is Zig from 1.0?
5 years from now. That's what we used to say also 2-3 years ago. It's going to be a while, but Zig is going to be interesting for people even before it reaches 1.0. So don't get baited by the number. The number is just a number. Zig is going to wait. It's going to have like a slow rise to 1.0. We're going to wait a while before we tag 1.0. So it's not going to be a Rust. It's more going to be like similar to Go, for example, where they waited a while before tagging 1.0, while Rust instead did it pretty early, and then they have a way of maintaining retrocompatibility. In our case, we kind of want to target 1.0 once we're really done with the language. So you will totally find a usable language, very stable, production ready, way before we hit 1.0. So like, look at the features, follow the development. Don't look at the number. The number doesn't tell you a full story. It's like it's just 2 digits or something like that.
Okay, a bit more general question. What will developer users experience if we don't distribute wheels and they don't have Zig on their computers?
Well, the point is that you put Zig as a build dependency. So like you use Zig lang, the Python package, in your build script. So for them, it's still going to be pip install foo, pip install whatever you're building. So they don't need to have it installed on their own. The whole point is that this whole thing can be made self-contained through the Python package manager.
C is complex due to its diversity in ecosystem. Does Zig solve that? What are the caveats?
So C is very complex for its diversity. Well, so for what I presented in this talk, we're not getting rid of C, right? We're keeping it. So what Zig does is try to help streamline some, in my opinion, bad decisions that have been done in the past in terms of C++ toolchain that were never fixed, like defaulting on depending on everything on the system. I think that's a lesson that also Python itself learned, right? From going from like system-wide installation and everything to virtual environments, etc. That's the main one. As for Zig, the programming language, if we imagine that you're using a C library from the Zig programming language, or you're writing your own C application, there are quite a few language features that help with that. My personal favorite is alignment. I'll just mention one, alignment. Alignment exists, can be, it doesn't matter all that much on big PCs, but like on the meta devices, it does matter more. And boy, do I hate, like when I was learning this stuff, I hated that in C, you don't see it almost anywhere. It exists, but it's not nowhere. Alignment, memory alignment.
You have to be,
Jesus.
your memory addresses have to be aligned to a certain system.
Yeah.
No, to certain bytes. So you can be aligned to 1 byte, to 2 bytes, to 4 bytes.
Yeah.
That depends on the
So
data.
some instructions expect your data to have to have the address that you pass to the instruction to be a multiple of a certain number. If that's not the case, like if you put your data in weird places, then either the instruction is not going to work, or it's going to have to fall back to a slower implementation. And this, as I said, this can, and sometimes it doesn't even work. Like for some architectures, you straight up get an exception, like a CPU exception. In Zig, alignment is part of the type system, and it's awesome. Now I can understand it, now I can make sense of it. There are plenty of things like this in Zig compared to C and C++.
Antonio this morning during the keynote was talking about alignment somehow, right? I think he was talking like data-driven design.
Yeah, data-oriented design. Alignment does come into play there because what you do there, what you do with data-oriented design is like you try to pack things together, and alignment can also feature into that. Yes.
No more questions online. Does someone want to ask, like live?
Can you say something about reproducible builds on Zig?
Yeah, so I don't believe that right now Zig is capable of making fully reproducible builds. I do think this is absolutely in scope. So I cannot make any promise on the state of today tooling, but yeah, we do care about this. So I mentioned consistent. I wanted to say reproducible, but yeah, we're not quite there yet. Oh, I have no idea, actually. Yeah.
Just wanted to add a quick note about the build time dependencies. So if you use pyproject.toml, there is this build section table. So if you use Zig to compile like a custom setup of Py file or something, you add Zigland or something in the build section. So when you pip install stuff, it goes through the PyProject and it sees that it needs to install Zigland, but it is not part of your library's dependencies, just at build time. So if it would be installed in a specific environment just to compile the code on your machine, and then that's okay. So your user do not need to depend on Zigland, nor your packages is made bigger just because it needs that.
Thank you. Okay. Oh.
Just a curiosity, because I don't know that much about Zig. How much is the Zig toolchain dependent on the Zig language, in the sense of how much is the language part necessary to run the full toolchain and compiler and whatever?
Yeah, great question. So if you're just using Zig CC, 0. If you're using the Zig build system, a Zig build script is written in Zig, so you will have to write Zig. This is like a bit of a nitpick, like a small nuance thing, but Zig also has its own compiler RT, and that one is written in Zig. So probably like if you're targeting a CPU that doesn't have hardware, I don't know, floating point instructions, and so you have to provide like a software implementation, you will get a Zig implementation. It doesn't matter to you, like you're never going to see that code practically, but that is also the last bit of Zig stuff that bleeds into the toolchain aspect of it.
Any more questions? That's it then. Thank you very much.
Thank you.
Yep.